Okay, the next concrete class of map that I really want to evaluate today is going to be the TreeMap concrete class. And again, similar to how the set interface had a tree set that had very specific benefits over hash set or linked hash set, TreeMap is going to offer the same kind of benefits to a map interface that linked hash map and that hash map don't have. And this really, if you remember, is going to be that trees are sorted. So a quick overview is that we'll have a quick introduction of what TreeMap class is. We'll look at the hierarchy, the class declaration, the features of the TreeMap, the constructors of the TreeMap class, the methods for TreeMap, some example code, and when we might want to use the TreeMap, and some key points about all of our concrete map classes. So a quick introduction, TreeMap in Java is a concrete class that is a red-black tree-based implementation of the map interface. So we won't go into much detail about what a red-black tree is. That is something that you will cover in data structures, but when you do learn more about the implementations of trees, then you'll know in the future when you use a tree map that this is using a specific implementation of red-black trees. So it provides an efficient way of storing key value pairs in sorted order automatically and allows rapid retrieval. So TreeMap implementation provides a guaranteed log n time performance for checking, adding, retrieving, and removing operations. A log n performance is very good. It means that as your data set grows in size, you're not doing a linear growth on the amount of operations it takes. It's actually it's logarithmic. It's really good performance, which again you'll learn more about the being able to compute these performances in the next class in data structures. So the two main differences between hash map and tree map is that a hash map is an unordered collection of elements, while tree map is a sorted in the ascending order of its keys. And the keys are sorted using comparable interface or the comparator interface. The hash map allows only one null key, while tree map does not allow any null keys because everything is sorted. And the null value is used as a sentinel value on whether something's sorted or not, or in the tree or not. So we can't add a null value. Doesn't make sense for sorting purposes. A quick examination of the hierarchy of our TreeMap class. So our TreeMap is a subclass of the abstract map, which implements the map interface. And then the TreeMap implements the navigable map, which is an interface, and that extends, that's a sub interface of the sorted map interface, which itself extends the map interface. And so the TreeMap also implements clonable and serializable, so it can get member of those two things, that we can potentially clone it and we can potentially serialize it and save it or send it over the wire. So TreeMap is a generic class that can be declared as follows. It's a public class TreeMap. And again, in generic form, it uses a key value pairing where K would be the type of key and V would be the data type of the value. And that's going to extend the abstract map, which itself is a generic form, TreeMap would also implement the navigable map, which has a generic form. And then it would also have membership to clonable and membership to serializable. So some of the features of our TreeMap that are worth mentioning: the underlying data structure of a TreeMap is a red-black binary search tree. The TreeMap contains only unique elements as its keys. The TreeMap cannot have a null key, but it can have multiple null values, because with maps, we only care about the sorting and the uniqueness of keys, and what the reference is, we don't care. Tree maps cannot have a null key, but can have multiple null values. TreeMap is not synchronized, which means it's not thread safe. We can create a synchronized version of the map by calling on collection synchronized map method. TreeMap in Java maintains ascending order. So the mappings are sorted in TreeMap either according to their natural ordering of the keys or using a comparator object that is provided using the object creation of TreeMap inside of its constructor. TreeMap determines the order of entries by using either a comparable interface or comparator object. And so the iterator returned by TreeMap is fail fast. That means we cannot modify our map during iteration. Okay, so a quick look at some of the constructors of a tree map. We have the default constructor, which is just tree map. And so the constructor is used to create an empty tree map that will be sorted according to the natural order of its keys. And all keys at its tree map must implement comparable interface. So the important thing here is if you're using a user-defined key, like a class that you make yourself, then you have to make sure that your class implements the comparable interface if you want to put it into a tree map. And so the compare to method is inside the comparable interface is used to compare our keys in the map. If you put a string key into the map whose type is an integer, then the put method will throw an exception name, class cast exception. Okay, let's look at another constructor. Let's look at the constructor where we can pass in a comparator object. So this form of the constructor is used to create an empty tree-based map, and all keys inserted in the map will be sorted according to the given comparator object. So the compare method in the comparator will be used to order the entries in our map based, again, on the keys. We also can have a constructor on our tree map that can take in as a parameter a map object. And so this form of the constructor is used to initialize a tree map with entries from the pass-in map, and the sorting will be according to the natural order of those keys. And then finally, the last constructor for TreeMap will allow you to take a data type of a sorted map. And so this constructor is used to initialize a tree map with the entries from the sorted map, which will be sorted according to the same ordering as the sorted map. Okay, let's look at the methods in TreeMap. And TreeMap has a decent amount of methods. So we have a clear method that allows us to clear all the entries in our tree map. We have a put method that allows us to put a key value pair into our tree map. We have a put all method that allows us to take a map type, map container, and pass that in, and it'll add all the entries from that map into this map. We have a remove method where we can pass in a key, and it will remove that key value pair, remove that entry, and it will return the value for both put and remove. It returns back the value. Also with get, where we have a get method, we can pass in the key value, and it will then return back the value associated with it. I can query the tree map for the first key, because remember, it's sorted. So this will give me the first key inside of my tree map. And then last key will give me the last key in sorted order inside my tree map. I can query my tree map to see if it contains a key. That'll give me a true false value. I can query my tree map if it contains a value as well, which gives me a true false. I can check the size of my tree map, which will give me an integer. I can get back the key set, so the set of keys. I can also get back my entry set, so the key value pair, so the entry objects. I can also get back the collection of values that are held in my tree map. I can invoke the comparator method, and this is used to retrieve the map's comparator, which is the thing that arranges the keys in order, or null if the map uses the natural ordering of the elements. So remember, this is an object that can do the task of ordering for us, but TreeMap can also rely on objects that implement comparable interface to naturally order themselves. I can clone the tree map. I can get the ceiling entry. So this method returns the key value pair having the least key greater than or equal to the specified key, or null if there's no such key. So this works just like the ceiling entry, or the ceiling value from the set. Let me see. And so that will return back. And so that's going to be the entry there. And then here, ceiling key. Okay, yeah. So I have the first, let me go back. This was the ceiling entry. I have another similar method called ceiling key that, given a key, will return the ceiling key of that. And so that's going to be a method that returns the least key greater than or equal to the specified key, or null if there's no such key. So both ceiling entry and ceiling key methods will throw a class cast exception if the key cannot be compared with the current key in the map. And they'll throw a null pointer exception when the key is null, because the tree map does not permit a null key. Very similar to the tree set, we also have the ability to do a descending set, a key set, and a descending map. So the descending key set will return a reverse order navigable set-based view of the keys contained in the map. And so the iterator of set returns the keys in descending order. And it's going to be a similar thing here with the descending map. It returns a reverse order view of this map, because the default view is in ascending order. Here, I can also get the first entry. So this returns the key value pair having the least key in the map, or null if the map is empty. I can get the floor entry. So just like I had a ceiling entry, the floor entry returns the key value pair associated with the greatest key that's less than or equal to the specified key that we pass in as a parameter, or null if there's no such key. And there's also the, very similar to floor entry, they have floor key that does the same thing, but for a key that gets passed in and returns back the key, as opposed to the key value pair, the entry object. I can get the head of the map, so I can pass in a key, and this method will return the key value pairs of the portion of the map whose key are strictly less than the key that's passed in. Head map, where I pass in a key and whether it's supposed to be inclusive or not. So these are essentially giving me submaps, just like I could get subsets from tree set, I can get submaps from tree map. So if I want it to be inclusive, it's going to be the very similar to this method, but it will include the element as well, the 2 key value that's passed in. I can check for higher entry. So this method returns a key value pair or mapping corresponding to the least key strictly greater than the given key, or null if there's no such key. Or I can also do higher key. So again, higher entry and higher key are very similar. It's just one's returning the entry object, the other will return the key object. And so this is used to retrieve the least key that is strictly greater than the specified key, or null when there's no such key. So it's like effectively all these are doing, just like the other ones, is if I pass in a key, it's going to look for the next key that would be higher than the key I pass in here that's part of my map. And then I can get last entry, which will return the key value pair that's corresponding to the greatest key in the map, or null if the map is empty. Lower entry, where I pass in a key, this method returns a key value pair associated with the greatest key strictly less than the specified key. So here I'd pass in a key, and that's going to look for the key, the next key that's lower than the one that's passed in as this parameter that actually exists in the map. And not the key, but the entry of that. So it's going to look for an entry that's lower using that key. But then we'll also have lower key. So again, similar method. It just depends on whether we want the key value pair or just the key. We have the navigable key set. So this is going to return a navigable set view of the keys contained in this map. Then we have the ability to pull the first entry or pull the last entry. So remember, pulling actually changes the state of our map. So if we do pull first entry, it will remove and return the key value pair corresponding to the least key in this map, or null if the map is empty. And pull last entry will remove and return a key value pair corresponding to the greatest key in the map, or null if the map is empty. We have the ability to replace so given a key, we can replace a value with a new value. And if we do that, we will return the old value from this method call. We can also replace with a key. And if we pass in the old value as a second parameter and the new value as a third parameter to overwrite this old value, it'll instead give us a Boolean value of whether it was successful or not. Here we can get a submap where we pass in a key. From that key, we pass in a Boolean value, whether we want to be inclusive of this first parameter. We have a third parameter, which is the key we want to go to for our submap. And then again, another Boolean value, whether we want to include the to value. So we can be inclusive or exclusive for either the from and to, and that'll give us the subsection of key value, produce a submapping between those two values. And so I can either get this submap either as a navigable map or as a sorted map. So either of those data types. I have a tail map. So again, this will create a submapping of my map, of my tree map, where I pass in a from key, and this method will return the key value pairs whose keys are all greater than or equal to the from key. So again, it returns back a collection. This will also return a collection. I can get that back either as a sorted map or navigable map. Excellent. Are there any questions related to these tree map methods? Because there's a lot of them, but they're pretty similar to the tree set methods. There's just more redundancy because they give you options on whether you want to do things based off of the key value pair, the entry, or whether you want to just do it as the key. Okay, so let's take some examples. Let's look at some examples of these tree maps. So let's look at a program where we create a hash map, a linked hash map, and a tree map objects, and see the order of entries of those maps. So here we'll have our source code, but what I'll do here is let's go to our TreeMap tester, and let me close out these others. Okay, so here's our TreeMap tester. So what I'm going to do is I'm going to import the concrete class of hash map. I'm going to import the concrete class of linked hash map. I'm going to import the concrete class of TreeMap, and I want to compare all of these. So I'm going to create a new public class TreeMap tester1. It's going to have a main method. Inside of here, I'm going to instantiate a new hash map that has a string value pair. I mean, a key value pair where the keys are string and the values are strings. I'm going to put the string R as the key, and then red, and then G for green, and B for brown, and O for orange, and P for pink. And notice I'm going to use double quotations because I want these to be strings and not characters. Then I'm going to look at the state of my hash map. Then I'm going to make a new tree map, and I'm going to pass that hash map into the constructor because I can pass another data type of map that's a valid constructor. And I'm going to save that into a tree map variable. And then I'm going to check the state of my tree map here. Then I'm going to make a linked hash map that's going to be a key value pair. And I'm going to put into there the same set of elements, right? R for red, G for green, B for brown, O for orange, and P for pink. And I'm going to print out my my linked hash map. And then let's see what this looks like. Let's go ahead and run this. And we're going to see that in our hash map, our elements are put, our entries are put in no particular order, right? P for pink, R for red, B for brown. So they're not in alphabetical order, and it's not an insert order either because we would have put red first. It's in just some random order. Okay, now if we look at the ascending order of our keys, notice it's in natural ordering, and for strings, that's in an alphabetical ordering. So now B for brown, and then G for green, O for orange, P for pink, and R for red. So this is my tree map ordering. And then for my linked hash map, recall that maintains the insert order by default. So here we put red in first, and then we put in green, and then we put in brown, and then we put in orange, and then we put in pink. Okay. So the next sample program that I want to explore using the tree map is to create a program to perform the add, remove, and replace operations in our map. So let's actually look at this in the IDE. So here I'm going to import my concrete class of TreeMap. And then here I'm going to create a class, TreeMap Tester 2. I'm going to create a main method. And then I'm going to create a new variable of data type TreeMap. And I'm going to use the generic form to define as my keys the string data type, and my values will be integer data type. And then I'll instantiate a new empty tree map. I'll query my tree map for its size, and I'll print that out. I'll query my tree map on whether it's empty or not. Is empty, that'll return true or false, whether there's any entries in my tree map or not. Then I'm going to put some key value pairs into my tree map. So recall that my keys are strings and my values are going to be integers. So here I'll have John 25, Ricky 22, Deep 28, Mark 20, and Peter 30. Then I'll print out the state of my tree map. I'll remove the entry where the key is Mark, and then I'm going to print out the state of my tree map. Then I'm going to replace the value of Peter, which was 30, with 18. Now, remember, a tree map is sorted, so pay attention to the order of operations after we do this replace, and then we'll go ahead and print the value of that out. So if I go and run this code, we'll see that we have the initial size of our tree map is 0. The query on whether the tree map is empty or not is true. Then the entries in ascending order. So remember, we're ordering this not off of the value. We're ordering this based off of the key. So actually, our ordering shouldn't change at all. We'd have to put in a different key to get a different ordering. Okay, so here, so let's see. So we're ordered in our key. So Deep would be the first key, then John, then Mark, then Peter, then Ricky. And then after removing, what did we remove? We removed Mark. So that means we're going to have Deep, John, Peter, and Ricky. And here we just replace the value of Peter with 30 to 18. Okay. Okay, the third example that I'd like to show is showing some of the key value setters and getters and the contains methods. So these are all very popular things that you have to do with these container classes. So let's jump over into our source code. So here I'll go ahead and I will import the concrete class of TreeMap. I'll create a new class file for TreeMap Tester 3. I'll create a main method. Inside my main method, I'm going to create a new TreeMap instance, and I'm going to store it into a variable. In the generic form, I'm going to specify that as a key, I want the data type to be a character, and as a value, I want the data type to be a string. And then I'm going to put into my TreeMap some key value pairs and entries. So A for apple, P for parrot, C for cat, B for boy, D for dog. Then for my tree map, I'm going to get back the entry set, and I'm going to print out the state of my entry set. I'm also going to print out the state of my key set and the set of my values. And then I'm going to get back the element, the value that's held at the key of C, and I'm going to print that out. Then I'm going to query my tree map and say, does it contain the key B? And that's going to give me a Boolean value, true or false. Yes or no, it does. And then I'll print out the value. And then I'm going to query my tree map to see if it contains the value of apple. And that'll give me back a Boolean value, true or false. And let's actually run that and see. And so here are we get back our entry set, which are key value pair, right? A for apple, B for boy, C for cat, D for dog, P for parrot. On key set, we just get the collection of keys from our tree map. For values, we get our collection of values. So this is a set, this is an entry set, this is a key set, this is a collection. Data types. Here we're going to get back, when we do our get on the key of C, we're going to get back the value of cat. And then we'll query, does our tree map contain B? Yes, it does. Does our tree map contain the value apple? Yes, it does. Let's take another look at an example program based off of the ceiling entry, the ceiling key, the first entry, the last entry, and the floor entry. So here we're going to start looking at some of these more interesting methods that are kind of exclusive to TreeMap. In the previous examples, we've really been looking at what both linked hash map and hash map do, but looking at how it's unique to TreeMap because of its sorted order. But now let's look at some of these interesting things we can do with our TreeMap because of the fact that it's sorted, how we can start grabbing meaningful sub mappings of our TreeMap. And so I know maybe if the explanations were a little bit more convoluted as to what all those methods do. And again, they should be the same set of methods that are true in tree set. Seeing them in practice, I think, will be pretty helpful. So here, let's go ahead and import our concrete class TreeMap. We'll create a new class, TreeMap Tester 4. We'll create a main method. And in our main method, we'll go ahead and we will instantiate a new empty TreeMap instance. And here I'm going to specify that the key of my TreeMap is a data type of integer, and the value of my TreeMap is going to be a string. So after I've created an empty TreeMap, I'm going to put some entries into it. So a key value pair. So 25 to John, 22 to Shub, 30 to Ricky, 35 to Peter, 18 to Johnson. And then what I'm going to do here is let me run this so that we can compare the source code to the results. So here we're going to get the ceiling entry. So on my tree map, I'm going to get the ceiling entry for the key of 32. Now notice 32 is not a key, but it's going to give me the ceiling value that's closest to 32. So if I go to the ceiling entry, what that means is it's going to give me, it's going to look in here, and the next thing that's higher than 32 that is a member of this map is going to be this entry here, 35 and Peter, and that's what I get. I get the ceiling entry is 35 Peter. Now I can do the same thing, but instead of getting the key value pair, instead of getting the entry object, I can pass in that key and just get back the key that's the next highest based off of the one I pass in here. So if I pass in 32 and I'm like, give me just the key, then it's going to be just the value 35. And that's in fact exactly what that is there. Okay, so now let's look at this. If I go ahead and from my tree map query for the first entry, well, the first entry that's going to be inside of this tree map based off of the fact that it's sorted should be 18 Johnson. And we see that's exactly what we get back here, 18 Johnson. So then let's do the same thing, but let's request for the last entry. And so here, the last entry based off a sorted order should be 35 Peter, right? Because that's going to be the last key in sorted order. And we'll see that, yes, in fact, the last entry that's returned is going to be 35 Peter. And again, if we go back and look at some of these methods, there was a lot of them. Where was it? So contains, ceiling, descending, floor entry. Okay, so we have last entry here is what we're doing. And then we just saw first entry as well. So you could say that there's the examples from these methods. Okay, let me go back here. Okay. Okay, the next thing I want to show is the floor entry. And so for floor entry, we're going to pass in the key, the value of 31 here. Notice for floor entry, it doesn't have to be inside the set, just like with ceiling entry. It's going to return the next key that's actually in our tree map that is under the key we're passing in. So if we're passing in 31, the next one under that will be Ricky, or will be 30, which is the value of Ricky. And we see that's exactly what we get as our floor entry, the key of 30 and the value of Ricky. And of course, if I wanted to do floor key, I could, and that would just return back the next key under the value that I passed in that represents a key. Now, if I go ahead and query my my tree map for higher entry and pass in the value of 30, it's going to get me the higher entry of that is inside my tree map. So it's going to be Peter right here, 35. And if I do lower entry than 30, it's going to look for what's lower. So it's going to be 25, John. And if I go ahead and do pull first entry, that's going to return to me the first, and then it actually mutates the state. Let's actually print that out too. System.out.println. Let's actually print out the T map after we pull, because remember that mutates the state of our data structure of our map. So let's pull for the first entry, which, and then the last entry. So when we pull it, remember it's returning back the first element, but then it removes it. So when we look at the state here, Johnson 18, Johnson won't be in there anymore. And when we pull the last entry, it'll pull the one at the very tail end, the greatest value, but it also will not be part of the map anymore. The state of the map changes. So no, I want this one. Okay. And so here, yeah, after we pull, notice Johnson, if I now print out the state of my tree map, is no longer inside of the tree map. And if we pull the last entry, we get back the highest value, but now that's no longer in our tree map either. Okay, let's take one more example program where we look at the head map, the tail map, and the submap methods of both the sorted map and navigable map interfaces, because I know trying to explain those might have just turned into kind of word soup of sorts, but I think seeing them in action, you'll easily be able to see how we can use these methods to take submaps from our tree map based off of the head, tail, or some in-between point of our map. So here's our source code for that. And again, let me jump on over here to here we go here. So this, I'm going to go ahead and import my tree map concrete class. I'm going to create a new class, TreeMap Tester 5. I'm going to create a main method here. And in fact, let me run this from the get-go instead of waiting. That way I can refer to it. Okay. So the first thing I'm going to do is I'm going to, inside my main method, I'm going to create a new instance of TreeMap where using the default constructor. So it's going to be an empty TreeMap, and I'm going to declare as my key an integer data type and as my value a string data type. Then I'm going to put some key value pairs into my TreeMap. So here, 25 John, 22 Shub, 30 Ricky, 35 Peter, 18 Johnson. And then I'm going to display the current state of my TreeMap. Now what I want to do is I want to go ahead and invoke that method descending map, so I can get the map back in descending order. So remember, initially I have the map in ascending order. Then what I want to do is I want to call that head map method on my tree map. I want to give it the key that I want to get the head map from, and I want it to be inclusive of that key. So if I have 22, it will include that as part of the returned map. And so this will return the entries whose keys are less than or equal to the specified key. So that should return for me. So let's look at what's happening here. So first of all, I'm returning my sorted key map here, which should be a sorting of this. So it should be 18, and then 22, then 25, then 30, then 35. And so if I look, yeah, 18, 22, 25, 30, 35, perfect. Then what I want to do is I want to call descending map. And notice what that's going to do is it's going to then produce a map that's in reverse order. So here, 35, 30, 25, 22, 18. Okay, so for head map, this should return a whole new map whose entries are keys that are less than or equal to the specified key. And since I did inclusive true, since I added true as the second parameter, I'll also include this value of 22, which does exist inside of our map. That means our head map is going to be 18, because that's lesser than 22, and 22. So here we have our head map 18 and 22. Then the next thing I want to do is I want to try tail map, where I'm going to pass in a from key value. And then also I can decide whether it's going to include the value I pass in or not. And I will also claim for that to be true. So it does include the value of 22. So this will return the entries whose keys are greater than or equal to this specified key. So that should be returned back 20, this entry here, 22 Shub, and 25 is greater. So that would be 25 and John. And this would be greater, 30 and Ricky, and 35 would also be greater. So when I look at that tail map, yep, it's 22 is included because it's inclusive, and then the next greater size key, and the next greater size, and the next greater size. So that's the tail end of the map from a given value, from a given key. Then we can take a look at a submap, which is going to return all the entries that exist between the two specified keys. So from this key to this key, and I can decide whether I want it to be inclusive from this key and whether I want it to be inclusive to this key. So I'll select to not include the from key, but to include the to key, which means I should omit Johnson. And then anything between Johnson to 35, which is the end entry here, but including 35. So it should include inside of my submap here from and to inclusive, from inclusive, my submap, which is going to be 22. So here, let's also print out so that we can see the TMap. Oh, wait. I wanted to get back. Oh, well, doesn't matter. And then, yeah, here. So that's my submap there. I'm looking at the wrong line. Okay, so yeah, so that's going to emit my value of 18, and it's going to include 22, 25, 30, and 35. And then here, I'm going to use these first set that we were using. We were using the navigable map interfaces. So here we'll use the sorted map interface. So here we'll do TMap where we're not using inclusive or exclusive. So the difference between navigable map and sorted map is navigable map gives the option for including the to and from keys, whereas the sorted map doesn't give that option. So if you don't use the true value pair, if you just pass in a key and it's exclusive by default, then it will go ahead and call the sorted map versions of these methods. So on our TMap, if we want to sort, if we want to get the subtree, if we want to use the head map, get the head map using the key 40, then it'll give me everything that comes before the key 40, which is everything, because 40 is higher than any of our keys. So we're going to get everything 18, 22, 25, 30, and 35. If I do on my TMap, the tail map from 22, well, I'm going to get an inclusive for the for my tail map. So it's going to be 22 Shub, 25 John, 30 Ricky, and 35 Peter. And then if I do a sub map, everything between 19 to 25, well, that's going to exclude 18. It's going to include this. I have a 25. So notice I'll get this 22, but since I have a 25 here, and usually the way it works is inclusive is true when you start at it, and inclusive is usually default to false. It's exclusive when you end at it. So on our sub map, even though we have a 25, we're not going to include the 25 because that's our ending label. So we'll include everything up to what this is equal to. So we're just going to get that sub map of 22 because we don't have a value of 19. We don't have a value of 20. We don't have a value of 21. We do have a value of 22. We don't have a value of 23 or 24. We do have a value of 25, but we only go up to the value of 24. Excellent. So you could see kind of the nuanced difference between if we decide to declare whether we want to be inclusive or exclusive explicitly versus the default behavior. And again, by default, if it's a to key, it would be inclusive. And if it's a from key, it wouldn't be. Excellent. And so when might we want to use a tree map in Java? Well, tree map is slower than hash map, but it's preferred when you want to, if you don't want to use null keys at all, and if you need to have your entries be in a sorted order, in a sorted ascending order. And so just some key points is that a hash table is suitable when you're not working in a multi-threading environment. A hash map is slightly better than a hash table, but it's not thread safe. It's suitable in the order of elements is not an issue. A tree map is slower than hash map, but is suitable when you need the map in a sorted ascending order. And a linked hash map is also slower than a hash map, but it's preferred if you want to have the number of insertions and deletions happen in your map, and if you want to maintain the insertion order of your hash map. Excellent. So that's all I have to say about tree maps and concrete classes. But now that we've talked a little bit about tree maps and tree sets, and we've talked about this concept of ordering and sorting things, and that we now know that there's two data sets that we've looked at, two data structures we've looked at that have to implement the comparable interface or have a comparator object passed to it in order to perform that sorting duty. We'll move on to look at the comparable interface and comparator interfaces tomorrow or the next lecture. So is there any questions that you have about this lecture or about maps in general? If not, we will end today's lecture. I'm going to go ahead and end the Zoom section to go ahead and stop the video.